Meet Pete. Pete doesn't know it yet, but in 3 hours and 41 minutes at 7:43 a.m., he will be rushing his pregnant wife Abby to the hospital. He won't be thinking about whether his car is charged and able to safely cover the distance from here to there, because the engineers who designed and built Pete's car already thought all about it. SAE International assembled a team of engineers from all over the world to think systematically about the charging of Pete's car. These engineers developed a series of standards that made mass production of Pete's car safe, affordable, and environmentally sustainable. But Pete won't have to think about any of that. He's probably never even heard of us. And we're fine with that. Because in helping the engineers keep Pete's car fully charged and safe, we've done our job. Sleep well, Pete.
Well, welcome everyone to the Formula Chassis and Suspension Development Overview presentation. Thanks for joining us today. Big thanks to the SAE Detroit section, the Carolina section for hosting this event. I'm Tim Drotar. I'm your moderator. Little bit of background about me. I'm currently a lead engineer in the Advanced Vehicle Dynamics group at Stellantis. Prior to Stellantis, I spent 30 years at Ford Motor Company, working in the areas of chassis systems and vehicle dynamics for passenger cars and light trucks. I'm a member of SAE, 30 years or so, SCCA, and the Tire Society. I have a Bachelor of Science in Mechanical Engineering from Lawrence Technological University, and a Master's of Science in Mechanical Engineering from the University of Michigan Dearborn. Shameless plug, I also teach a couple of classes for SAE Professional Development, one entitled Advanced Vehicle Dynamics for Passenger Cars and Light Trucks, and the other one is entitled Fundamentals of Steering Systems. So before we start, I want to address a couple housekeeping items. All the participants are automatically muted with their camera off. We do encourage you to use the chat function to use it, ask any questions that you might have. You can start right now. I'll take your questions and ask them to the presenter at the appropriate time. Also, we may have time at the end for our speaker to answer any of your questions. Also, this presentation is being recorded and it'll be posted on the SAE Detroit section's YouTube channel at a later date. So today we're going to be hearing from Darrell Hancock Jr., who is a senior technical specialist in vehicle dynamics at Stellantis NV. Darrell will share with you his knowledge and experience in vehicle dynamics and chassis systems. He'll give you some really useful insights into the development of the chassis system for vehicle dynamics. He's going to talk about testing and tuning for improved handling, and hopefully, we'll have some time at the end to answer any of your questions live. So please type your questions into the chat. So Darrell, good morning, welcome. Thanks so much for being here.
All right, thanks for the introduction, Tim. Let me share my screen here and we will get rolling. Okay, so as Tim mentioned, I'm a senior technical specialist in vehicle dynamics at Stellantis. I've been here about 28 years now. Almost all of that was in vehicle dynamics. Prior to that, I had several other jobs, including as an IndyCar engineer back in the 1980s. So I got some background that hopefully I can share with you guys and help you with your Formula SAE projects. So again, please ask questions in the chat, and Tim will answer them if he can, or he can interrupt, or we can save them for the end. But I think the important thing is to answer as many of your questions as possible. So we're going to talk chassis and suspension development. We will start out more on the development side. You can go to the next slide, hopefully. So we'll talk about development in the beginning, right? Why it's important, what it is, how to do it. And then towards the end, we'll get into how to tune some of your steering and handling characteristics of your car. But I think this is the one thing I've seen as a Formula SAE judge, and even in my own experience, the developing the car, making sure everything works and works properly is absolutely critical. So hopefully this will help you guys out in planning the final stretch of your FSAE program for this year. Okay, so what is development? It's part science, part engineering, and part art. The science, it's mostly physics. It's F equals MA for a large part of it. And the engineering, you're applying that science to something real, to building a car. And part of it is art. And that comes in with you have a human driver in your car, and you need to satisfy that driver, tailor the vehicle's performance and efforts and everything to what a human being likes and can take advantage of. And there's no real hard set formula or equation to do that. It's art. And that's where, having the driver in the car and developing the car is really important, right? You can't do that virtually. You can't do it ahead of time online. There's no equations or anything. So that's critical, right? If the driver can't operate the car, then you're not going to have a very good result at the competition. And some people will say luck is a part of it. But there's a famous quote from Roger Penske: the harder you work, the luckier you become. And I won't deny that there is some luck. There can be bad luck and there can be good luck, but really, like Roger Penske says, the harder you work, the luckier you become. So don't just say, well, we had bad luck, we'll do better next year. No, figure it out and do something to make yourself luckier, right? And development is just an iterative, ongoing process, right? It never ends, right? You make your car faster, and then you think, well, I can make it a little faster. I can do this, I can do that. But at some point, you gotta go to competition and compete, right? And one of our chief engineers here at Stellantis used to say, well, it's time to shoot the engineers and start production on the car, right? Development's got to stop, and we got to start making cars. So the important thing is to make the best use of the time while you are developing the car. And that comes largely by planning and prioritizing and preparing, right? You've got a couple of time constraints, both how many man hours you have for your team and the days on the calendar before the competition, and you want to make the most of that. So the objectives in developing your car, and this really applies to any part of the car, the powertrain, the batteries, if you've got an electric vehicle, whatever, right? The first thing you want to do is validate the function, right? That everything does what it's supposed to do, to work or operate in the proper or particular way. Doesn't do any good to take a car to competition if the steering system doesn't work, right? You've got to make sure everything works the way you intended it to. And then the second thing is to validate the reliability of the vehicle. You want to have confidence that your vehicle is going to start up and run and complete the course, complete every one of the courses at competition. And if you can't do that, you're not going to score a lot of points. You're not going to have a good result. And then validate the durability. The durability requirements for Formula SAE aren't that high, but you do need to be able to go through the whole competition weekend without anything going wrong with your car. And then lastly, the thing that's more exciting and everybody gets more excited about is improving the performance of all the systems on the car, making it go faster, stop quicker, corner harder, whatever. So again, that's kind of the ultimate thing you want to do, is that last step, but you got to go through the first 3 steps before you can do that. Okay, so one thing you've got to keep in mind is that everything is a compromise. I teach a dynamics class here at Stellantis, and I tell them there's only 2 things you need to know. The answer to every question is it depends, and everything's a compromise. So there are always compromises, and your goal is to find the best compromise or find a better compromise than all the other teams that are competing. And there's a quote there from Patrick Head, pretty famous Formula One engineer. It's not the team that achieves the most horsepower or downforce that wins the race. It's the team with the best compromise of all the systems on that day that wins. So even at the Formula One level, it's still all about compromise and finding the best compromise. Okay, so what are your objectives when you're developing your vehicle? Reliability comes first, right? You've got to be confident. You've got to make sure that that vehicle is always going to start and run and do what it's supposed to do, right? You might have the fastest car in the world, but if it doesn't start at the beginning of the autocross course, you're not going to show anybody anything, right? And then the second thing to keep in mind is reliability always decreases as complexity increases. As you add more parts or systems or components to your vehicle, your reliability inherently goes down because there's more ways for something to go wrong. And then there's all the quotes there. It's been said many times by many different people that to finish first you have to finish the race. And some people said it differently. But you know, if the car isn't running on that last lap of the race, you're not going to win the race, right? So that's really critical. So that's why reliability and durability to a certain extent comes into play. But I will also caution you on that, particularly for Formula SAE, before you can finish the race, you have to start it, right? You have to have your car finished, you have to have it validated, you have to have the reliability in it, and you have to have the durability, right? So it's not just finishing the race, it's getting to the race with a car that's ready, that's prepared, that is capable of completing the competition. Okay, so I said before, reliability comes first. I don't know where you are in your studies, but at some point, you usually get a reliability, a lecture or two on reliability. So the reliability of any system is the product of the reliability of each part in the system, right? And these reliability numbers, these R values, are less than 1. You know, they're 0.99 for a 99% reliable part. So as you multiply these parts together, these are all numbers less than 1. The numbers become even smaller than 1. And then your vehicle is made up of a bunch of systems. And the reliability of each system, or the product of the reliability of all the systems, is the reliability of the vehicle. So for example, you talk about the frame in your car. It's pretty reliable, right? We don't see many frame failures, but you know, you may have fatigue failures. You may have a bad weld. You might have a fastener that comes loose, right? Those are all pretty high reliabilities there. So you multiply those together and you get 0.988 reliability. Okay, not bad. But then you also have your front suspension with more parts in it, more things that can go wrong. Multiply all of those reliabilities, and now you're only about 84% reliable. Then you have all these other things, and you multiply the reliabilities of each of these systems together, and you wind up less than 50% reliable. So that's why it's important to look at the reliability of every single part on your car, and not just the parts, but the assembly, right? Do I know I have this fastener tightened correctly, torqued to the right spec? Do I know that this connector is going to stay connected and keep water out if it happens to rain, right? So you can very quickly get down to this very low reliability number here. So that's why it's really important. And it's not glamorous, it's not fun, it's not exciting. That's probably not what you thought of you know, being involved in Formula SAE, but it's still very critical. Okay, so phases of development. There's the design validation, and you do a lot of that either virtually or on paper, right? You're doing some calculations, some analysis, maybe some simulation, failure mode effects analysis. That's something as a judge, I've never seen a team come in with a DFMEA of their car, but that's a great skill to develop and a great thing to have for your car, right? Have that failure mode and effects analysis. And you can make it as complicated or as simple as you want to, but going through it to some extent will tell you the less reliable parts, systems, components of your car, right, and help you improve that reliability. It basically just prioritizes things, and you go after the highest risk numbers for a failure on your car, and you do something to reduce those, and your reliability goes way up. So then the next step is you validate the components, right? Could be very simple. Did I make this part to the right dimension? Did I use the right material? Is that material strong enough? How much does it weigh? And then the function of the part. And whenever you can, test your parts as soon as they're done, right? If you can do some kind of bench test, right? If you can take your brake calipers and just pump them back and forth and make sure they don't leak and your connections are tight, that sort of thing. The more you can test up front before waiting to have the whole car put together, the better off you'll be. And then can you assemble your parts, right? Does it fit where it's supposed to? Does it interfere with somebody else's part that you weren't very clear with, right? Just to make sure everything as a part does what it's supposed to do and doesn't do something that it's not supposed to. Then you talk about system validation. Can you assemble all your parts into a system? Can you bleed your brake system when you put it all together, right? Does everything work? When I press on my brake pedal, do my pistons and my calipers apply the brakes, right? And does it do what it's supposed to? You know, anything, again, you can do to bench test, like a dyno test on an engine. Anything you can do to test those up front before you have the whole car done, that will put you ahead of the game. Then you get to vehicle validation. When you've got your whole vehicle built, either virtually or physically, validate that everything works together as a car, right? The brakes do what they're supposed to do. The powertrain drives the car down the road. The driver can fit in the seat. The steering efforts aren't too high that the driver can't steer the car, right? So validate everything, including the driver, right? The driver is part of the system. So you want to validate that. In the automotive world, we talk about either the V or the W model of vehicle validation. They're pretty much interchangeable, but you start out at the top left here, what we would call program objectives. Those would be your goals for your Formula SAE team, and the rules, right? You've got to meet all the rules. So that's one of your key objectives. And then, you know, what do you want your car to be? Are you going to try to perform well in every single event, or are you going to target certain events and try to perform absolutely the best and score points that way? Once you've got that, then you move down to the vehicle design. You start designing your vehicle as a whole, and then you design the systems that will work into that vehicle. And then you design the pieces, the parts that go into those systems, and you kind of put it all back together. So you move down this way, and then you'll do a virtual assembly in CAD, right? You'll start putting all the parts together, excuse me, and make sure they fit. You don't have any interferences or anything. Then you'll validate it virtually, right? You'll do some calculations, some simulation, maybe lap time simulations, that sort of thing. And you may find some discrepancies there, right? It's not doing what we wanted it to do, and you may cycle back into your vehicle design and change your design. But the more of that you can do on paper or on the computer, right, the easier it is. It's a lot easier to shift some electrons around than it is to scrap a big piece of metal that you spend a bunch of time manufacturing. So you may loop through that several times. You may go through this repeatedly, and that's not a bad thing. That's not a sign you messed up. That's a sign that you're already developing your car before it even really exists. Okay, so then once you've satisfied that and you've validated that everything works, at least in a virtual sense, you're going to go down here and you're going to start manufacturing and assembling your parts and your systems. And then again, if the more bench testing you can do on individual parts and systems, the better off you'll be when you will eventually build that up into a vehicle. And you'll have a vehicle in the automotive industry, we call it launching for production. For you, it's going to the competition, right? So the more you can step through this and even repeatedly, the better you will be prepared for the competition. And now this is showing the whole car, right? But you probably all have sub teams that work on different parts of the car. You probably have a powertrain or drivetrain team. You have a suspension team, maybe even separate front and rear suspension teams. I don't know. You have a team for the brakes. You have a team for aerodynamics. So you've got all of these W's going on in parallel, and they've got to feed back and forth, right? It doesn't do any good for somebody to design brake rotors that won't fit in the wheels, right? So you got to have communication, coordination, collaboration between all of your subgroups. And I've seen a few cases where that really didn't happen, right? Somebody made a really great part that didn't fit on the car, and there was no way to attach it because they weren't talking to the frame group to integrate it into the vehicle. So that's really important. And here in the auto industry, we call this vehicle integration, integrating all the systems into one vehicle that works as a whole. Okay, so once you've got your vehicle all put together, you have a physical vehicle, and you start developing that. That's what's really critical to success, right? A well-developed and tested vehicle has a much higher chance of success than a super sophisticated design that hasn't been proven out, hasn't been tested, hasn't found its faults and had them corrected, right? So the sooner you can get to that point, having a full vehicle put together to test, to develop, the more time you'll have to address anything you find that didn't work as you expected, right? No matter how much time you spend analyzing, simulating, modeling, there are going to be things that you just didn't find until you get to a whole physical vehicle. And it's an inexact iterative process, right? And it's difficult, takes a lot of resources, takes a lot of time, right? And those things are limited for you guys. You have limited resources available to you. So you want to plan and prepare and make the best use of those limited resources to develop your car, to make a better car. Okay, so how do you do that? Well, it's a lot of the, what you learned in like grade school: who, what, when, where, why, and how, right? You got to think through all those things and maximize your utilization of them. So it's not just putting the car together and go driving it around and seeing what happens. Every time you go drive the car, test the car, you need to have a plan, and it needs to address that who, what, when, where, why, and how. So start with a written plan for your test session, right? Each step, how long is it going to take? How many people are we going to need? What equipment are we going to need? What resources do we need? So start out with the why. What's your objective, right? We just got the car together. We want to test it. Maybe we just want to shake it down and make sure everything works appropriately, and the engine doesn't leak oil, and the transmission doesn't overheat, and that sort of thing. So that's a valid why, right? We just want to drive the car a little bit and get experience with it and see if it's okay, right? Or maybe you have cooling problems. Maybe you want to develop your radiator, your cooling system. That might be another reason to do some vehicle testing, right? Or your brakes. Optimize your stopping distance, to figure out the wear rate on your pads. Are you going to have to replace them at any point? Is the pedal feel good for the driver, right? So just some examples of the why. Why are we doing this here and now? Then the next thing is the what. What do you need to accomplish that objective, right? If you're going to test a bunch of different brake linings, well, you're going to need a bunch of different brake linings to test, right? And you're going to need your car. It needs to be prepared. You need to have the alignment and the ride height set. You need to check the tire pressures, the condition of the tires, all the fluids. If you've got an icy engine, right? Make sure everything is good. Car's got to be ready to go. Then you need to think about parts, your test parts, if you have any, wear parts, right? Are you going to wear out brake pads? Are you going to wear out tires? And then some spare parts, because things are probably going to go wrong, right? Especially early on in the development process. You need some spare parts, fasteners, that sort of thing. And the equipment, right? First thing to think about equipment-wise is safety. You need fire extinguishers, you need a first aid kit, you need communications, not only between the car and the pits, but also, well, if something happens, do we call 911? Do we know where to send the people, right? We say, well, we're out here testing, and the next thing, well, where's here, right? So think about that. You're going to need tools and shop equipment, and you may have some instrumentation, some onboard data acquisition. So those are the whats that you're going to need. And then the how. How are you going to do this testing to, again, go back to that why, that objective that you're trying to accomplish? How are you going to measure, decide, conclude that you've met that test objective, or maybe that you haven't and you need to go do something different. So a couple of approaches to take when you're out there testing the car: fewer and shorter runs. Having a smaller track or shorter lap will put less wear and tear on your car, give you less data to analyze from your data acquisition system, and you can get through more tests, right? You're typically going to run a minimum of 3 laps per test, 1 lap going out of the pits, 1 lap at speed on the course, and then 1 lap to come back in and slow down in the pits, right? So if those laps are shorter, either distance or time wise, you can get through more of them in a given amount of time, right? The other option, though, is to do more runs, more repetitions, run 4 laps, 5 laps. Your driver will get more familiar with the car and more familiar with whatever change you made. He'll have more confidence in whether that's a good or a bad change, right? And you'll see more variation in your vehicle, right? It'll burn more fuel, or the batteries will get drained down a little bit. You'll see some tire wear, some brake pad wear, that sort of thing. And that variation is both good and bad. It's bad that it may cloud whether or not your change was a good one, but it's good that that's the real world, right? When you're at competition, you're not always going to have a full tank of gas, right? Your batteries aren't always going to be fully charged. You will also get more data from more runs, which can be good and which can be bad. Sometimes analyzing the data can be a chore and require a lot of time, but you have more data. You can edit out, well, I know I made a mistake on that lap, so don't use that data. So it's both a pro and a con there. You won't get through as many tests, right, if you spend more time out there running on the track, but you get better evaluations, right? More chances for the driver to give their feedback. So how are you going to measure the performance? That's kind of a big one to think about ahead of time. You can use onboard data acquisition. Some teams have some really sophisticated data acquisition systems, but a stopwatch is just fine, right? That's the ultimate bottom line, right? It's what is my lap time? That's what you're trying to accomplish. So something simple like a stopwatch is very valuable data. And also the driver feedback. Did the driver sense the change? Was it positive? Was it negative? Did it have some pros and some cons, right? Driver feedback can be a great metric to use. The bottom line is probably the stopwatch. Your data acquisition can give you some more details and information to dig into. And the driver feedback will be a great all-in-one summary of the car, right? We're great at measuring things, data acquisition, but they don't always give you an answer. Whereas the stopwatch and the driver feedback will give you an answer. Right? Think about changing conditions, right? If the weather changes, if the wind comes up, if it gets hotter or colder, how are you going to adjust for that, or at least record it? And then how often are you going to refuel, charge your batteries, replace parts, that sort of thing. That's something you got to consider. Okay, and then the where of vehicle development, where are you going to do it? What kind of course do you want? You don't want to have it to be really severe, really long laps, because you're putting wear and tear on the car. You'll have less data to analyze with a shorter course, right? And you can do more things, right? You got to think about what space is available to you. Some of you may be able to use a go-kart track or a race track, or you may be able to use a parking lot at your school somewhere, right? What space is available, and make the best use of it. What else do you need in terms of location? You need the pits, right? Some place to park your trailer or your truck or whatever. You may need power. You need to have spotters and places for them to watch the car. Do you need compressed air, water, fuel? You need something to mark the course, cones or flour to put down to make a path. And then even you need bathrooms, right? Somebody's going to need a bathroom sooner or later. You may need lunch and drinks and all that. Little logistics there that can be a big effect on how well your testing goes. And again, you got to think about safety. Always give yourself a lot of runoff room, right? Especially early on. This is a car that a bunch of students put together. Maybe your first time for a lot of you putting a car together. So, expect the unexpected. Give yourself, plenty of margin if something breaks on the car or goes wrong. And you want to have spotters, usually not a problem, but never let the car out of your sight. When I was doing Baja in college, we watched the guy drive a car off into the woods and then it didn't come back. And we didn't really know what was going on. Did he just drive further into the woods or did it break down or what? Right. So we probably should have had somebody out there along the whole route to know what was going on. And then again, think about if the worst happens, how do you get help there, right? How can you direct the fire truck, the ambulance to where you are? And that's a little unnerving to be thinking through that, but it's important to do. Okay, and then the who of development, you need to have people with assigned roles and you need to have enough people to fill those roles. So you need to have one person that's kind of in charge, right? The crew chief or the engineer or whatever you want to call that person, right? They make the decisions, they take notes, they make sure everything's going well, right? Then you need to have a driver or drivers. Hopefully you have experienced drivers that have gotten some experience, maybe running autocrosses, maybe driving last year's car, maybe went to competition last year, right? You need to have a consistent driver, not one that can just occasionally out of thin air reel off a fast lap. You need somebody that can drive consistently and fast, and that they can be sensitive to changes. Some drivers are not good. They just go out and drive the car and get everything they can out of it, and they don't have the ability to give feedback. Other drivers can basically play back a videotape in their mind of what went on in the lap. And that's very important, especially when you're testing. Even if that driver is not quite as fast as another one, getting that feedback is pretty critical. That acquisition, if you have that on board, that's great. Think about doing somebody on the spot doing at least some analysis of the data as you're running, but then afterwards, probably a more thorough analysis. You'll need mechanics or crew to take care of the car. And again, spotters and safety crew to make sure nothing goes awry or to react if it does. And then you always need some spotters, some, I guess, extra people around, right? Oh, we left this part in the garage, go get that. Or, well, it's getting to be lunchtime, who's going to go pick up the pizza, right? That kind of thing. There's always unexpected things that come up, and having a couple extra people to handle that's really good to plan on. Okay, the when to test, how long and how often. Testing should be included as milestones in your overall schedule for your vehicle, right? You need to have planned tests as you get closer to competition, and test as early as you can, but only when you're really prepared. Don't test just because the calendar says you're supposed to test. If the vehicle is ready, you've got the parts, the weather is conducive, then test. But the earlier and more often you can test, the better, right? And I've said it before, the bench testing is much easier than vehicle testing. And you can save a lot of your vehicle testing by finding the problems early, testing the parts and systems on their own before they go into the vehicle. You want to test early enough to allow time to fix things you find wrong, right? If you run a test 2 days before the competition and find something is way off, that doesn't give you much time to react, right? So test early and plan on, after we test, then we're going to have to fix things or improve things or change things. And early on in the program, don't plan on testing for a full day, right? You're going to have problems with the car. You're going to have parts that break, something comes loose, something doesn't work the way it's supposed to. And you may have to just cut a test session short, go back to the shop. But don't let that get you down. You're finding reliability or durability issues, right? And now you've got the chance to fix them. And then as your development program goes on, extend your test duration, and ideally, a couple of weeks before competition, you would basically hold your own competition, go through all the events and see how you perform, and then give yourself a couple of weeks to try to improve the vehicle, fix anything you found in that final test. And then remember, schedules are important, timing is important, but you control it. Just because it says on the calendar we're supposed to test today, if the car isn't ready, don't drag it out there, without an alignment and test because the schedule says to. Do what makes sense. Timing and discipline is certainly important, but it's most important to do things right. Okay, once you've got that test session using all planned out, the who, what, when, where, why, and how, make a schedule for it. start at the very beginning with, packing up the parts, getting the car aligned and getting the tires aired up, that sort of thing. And then think through that schedule and see how you can shorten it up. How can you improve it? Can we have different groups doing different things in parallel instead of in sequence, right? And then think through how you're going to test the car, right? If we're going to change our acronym on the car, do we need to realign it? That's going to take some time. So maybe we do that last. And then think about contingencies, right? Things are going to go wrong. What if it rains? What if you have a flat tire, right? What if something goes wrong? Can you salvage it? If it rains, do you have your rain tires with you and you can start working on your rain setup, right? So think through things that could go wrong. So now you've got it all planned out, you're ready to go, and the practical side of it comes in, right? That it always takes a lot of resources to do a development program. So make sure you get the most out of it, make the best use of those resources. So do your homework up front, right? Don't just, well, we'll just test that part and see if it works. No, do some calculations, simulations, tests, something to know that, yeah, it's worth tying up the time on the car to test this part. It's not just a, well, we'll try it and see, right? No, this has a good chance of working. So we want to devote test time to it. And Claude Ruel, who you're probably all familiar with, he says there are too many parameters, the car, the track, the environmental conditions, to be spot on in your calculation. You work it in delta or change and trend and sensitivity. So you can never get the answer purely by simulation, but you can get a lot of answers. You can find bad answers for sure. You may not find the very best answer that way, but you can find the ones that are likely to work and the ones that aren't. So that's important to do up front. And so if you're methodical and meticulous in your planning, you will get good results and data that will help you the most. So if you have a vehicle left over from last year's competition, make use of that. You can maybe put some new parts or systems on it and validate them ahead of having this year's car done, right? You can get some miles on your new brake system or whatever. And you can also use it to train and select your drivers, get them comfortable driving that car in those kinds of courses. And because you really don't know ahead of time what the competition is going to be like, you won't know till fairly later on what the course is going to be. You don't know what kind of pavement it's going to be on, right? So it's hard to have absolutes. But if you target, well, I want to be able to go through an autocross 10% faster than I did in last year's car, there you've got it. You can take last year's car through it, then you can take this year's car through it and see how much better it is, right? So that can be a valuable asset, although it does take some of your resources to keep that last year's car running and operating. But that can be a really good tool to have. Right, so the objective again of development is to validate function, reliability, and durability, and then improve the performance of the vehicle. So when we talk performance, from a chassis standpoint, I'm not going to address powertrain. That's not my area of expertise. You've got 4 criteria that again are a compromise. You want your handling balance, right? You want understeer, oversteer to be appropriately balanced. You trade that off with total grip, and then you want responsiveness. You want the car to respond to the driver's steering, but you also want it to be stable so that the car doesn't steer on its own, right? So you're balancing these 4 things, and you're trying to strike the best compromise of all of these things, right? And then you have to achieve that under steady state and transient conditions, in combinations of cornering and braking, cornering and acceleration, and at different speeds and potentially even different weather conditions, right? So again, you're going back to trying to find this best compromise of a lot of different things. So one little tidbit I'll say, when you're tuning to improve the performance, you're probably going to check your tire temperatures. The goal is not to optimize tire temperature, nor even alignment settings or downforce or brake balance. The goal is to minimize your lap time, right? The faster you can turn a lap, the better, even if your tire pressures or your tire temperatures aren't optimal, right? If they give you a better lap time, then that's the better tire temperature to have. And you will run into some circumstances where you add a part or make a change to the car, and it gets slower in part of the track and it gets faster in another, and the driver won't be happy with it because it slowed down in one spot. But the bottom line is lap time. If it slows you down the straightaway, but it makes you faster in the corners and your overall lap time goes down, then that's a good change, one you want to keep. Okay, you always want to know what you're testing. And this is, again, not the glamorous, exciting thing, but always know what parts are on your vehicle, what the spring rates are, what the weight is, what the alignment is, you know, what the wing angles are set to. And then you want to know all your parts, right? What are the valve codes in your dampers? What are the settings on your dampers? What tire pressures do you have? What tire pressures did you start with cold and what are you running with hot? How many laps are on your tires, right? Tires will wear out and your lap times will get longer as the tires wear. So keep track of that. I guess tire pressure is really important. It's listed twice there. And check these things before you test, right? Typically we have a setup sheet, right? Here's what the car is when we left the shop. Here's what the alignment is. Here's what parts are on the car. Here's what the damper adjustments are, right? And then you can always go back to that if you go crazy in your testing and something seems wrong. So have a form to record that and save a couple copies of it, right? Whether it's an Excel spreadsheet or a paper form, whatever, always have backups. And always have enough information on hand to be able to unwind whatever change you made. You went 3 clicks higher on front rebound damping and that didn't work. So you need to be able to say, yeah, it was 3 clicks up. Let's go 3 clicks down to get back to the previous setup that was better, right? So you need to document all this. And it's not exciting, it's a little meticulous, but there's probably somebody on your team that is good at that sort of thing. So that's a good job for them. Okay, and then record the environment you're testing in. What location, what surface, what the surface temperature is, what your course layout is, so that when you come back for another test session, you can compare your data and know that you really got faster or not. Maybe you didn't get faster because it's cold outside and your tires weren't warming up. But if you know you're using the exact same test course, then you eliminate that variable, right? And keep track of the weather. I've seen a couple of teams that actually have a weather station in their trailer, so they know exactly what the weather is there. You don't need to go that far. You know, you use Weather Underground on your cell phone, and you can get pretty localized weather that way. And just record that. That may come in handy later. Okay, and then keep a record of every single test run. When the car moves under its own power, you need to write that down, right? And if you've got a track set up with laps, right, keep track of the lap time. You know, how many runs did you do? And then when the car comes off the track, you know, make a note of that. You want to have a history of everything that car's done. And then record along with that the driver feedback. The best way to do it is get a map of the track and have the driver step through it. You know, what did it do here at the entrance to the turn? How was it in the middle of the turn? How was the exit of the turn? Now in the next turn that was bigger and faster, how was the car, right? That's the easiest way to record that. And then you'll have some external measurements, your lap times. Maybe you set up some trap speeds, right? Or you time over a certain segment of the course, right? This is all important data to have and record and keep organized. You'll have your onboard data acquisition, right? All that data, but it doesn't do you much good to say, oh yeah, look at this, this is fantastic, you know, but you don't know which lap that was and what parts you put on the car to achieve that, right? So you need to synchronize all that data with the lap sheet or lap chart, right? So that you know what gave you the results of that data acquisition, right? Check and record your hot tire pressures and keep track of your fuel level or how charged your batteries are, right? And then for a lot of the parts, they're wear parts that will wear out. Keep track of how many laps are on each set of tires, each set of brake pads, that sort of thing. Your clutch, if you've got one, right? That's a good thing to know so you can track when it needs to be replaced and repaired. Okay, data acquisition, I won't go into a lot of detail here. It's good to have, but don't go overboard, right? Don't acquire data just for the sake of acquiring data. think about what you want to know, what information you want, and you generally can't record that directly, but you'll have to record a few channels that then you can analyze and combine to give you real information. You know, data is just ones and zeros on a hard drive somewhere. Unless you can turn that into information, you know, engineering units, something you can use, it's not a big help. And again, you know, make sure it's tied into your lap chart, so you know, this lap at this lap time, here's what my maximum lateral acceleration was, or whatever you're interested in. Okay, again, we talked a little bit about the driver. You need a fast and capable driver, but they also need to have self-control and patience to evaluate each change, not just say, well, that was no good. Why was it no good? What could make it better? You know, that sort of thing. They need to be objective and not have any favorite parts. Well, I designed this wing, so I know it's going to be good, and I'm going to say it's great, right? And then if the car has some shortcoming, you know, a good driver will find a way to drive around that. But when you're testing and developing, you don't want that. You want to fix that shortcoming, not just deal with it, right? Okay, so your course, how are you going to test? You should either be trying to test a particular attribute, like stopping distance. You just need a straight line, right? Or it should be somehow related to what you're going to do in competition. You want to keep the course simple. Don't, you know, set up a full-blown autocross course. That takes a lot of time and puts a lot of wear and tear on the vehicle doing laps around that. Try to keep it simple, right? Eventually, later on, you may want to do that, but initially, you want to keep it simple. And you don't need to go beyond what the competition course will be, right? You don't need a 100-mile-an-hour corner, because SAE is not going to throw that at you, right? The insurance company gets real nervous about that. So be realistic, right? And document the course so that you can set it up later. And also that may help in your data acquisition, knowing what the radius of the turn was, right? So now you're out there, you're got your course set up, you're ready to go. The first thing you want to do is warm the car up, make sure everything's right, tire pressure's set, and drive the car slowly, especially early on. You know, you've taken the car apart, put it back together again, right? Sneak up on things. Check that the brakes, you know, the driver should apply the brakes hard from a slow speed and then increase the speed and try it again, so that the driver is confident with the steering, right? Same thing, well, confident with the brakes, and then the same thing with the steering. Steer back and forth at low speeds. Don't, you know, commit to a high speed turn and then realize, oh, the steering efforts are too high and I can't steer it, right? Warm everything up, including the tires, do some gentle laps, progressively getting faster, and make sure everything is functional. Check the car out in the pits, make sure nothing's come loose, it's not leaking, nothing's getting too hot, right? The wires aren't laying on the exhaust system, that sort of thing. And then fix anything that needs to be fixed. So start out with acceleration and braking, right? Start with straight line tests. They're the easiest and the simplest to analyze, right? Leave yourself lots of room in case something goes wrong. So start from 0 miles an hour, accelerate and brake, and then do that from higher speeds, right? Excuse me. Monitor the temperatures of everything and see how fast things are cooling off, right? Make sure the driver has confidence in the car, right? Then you're going to move to steady state cornering. Not super exciting. You're going to be driving in a circle, right? But it's very important to get your steady state handling right before you can get anything else right. So you look at the typical Formula SAE autocross and endurance course, there's lots of corners, and a lot of them are long corners. They go through 180 degrees or more of angle, right? So getting through those faster is the important thing. And there's a quote from Maurice Ali, who's kind of the grandfather of vehicle dynamics. He says, don't let anyone persuade you that skid pad tests don't mean anything. They mean pretty much everything if you take the trouble to interpret them. So skid pad, constant speed, steady state testing, very important. That's the foundation. So the thing to do is look at your autocross and endurance course maps. If you've got them for this year's competition, great. If not, look at previous years, right? They're not going to be completely different from year to year. So figure out the tightest radius on the course, the smallest diameter turn or smallest radius, 1 or 2 radii that represent the kind of the average or the typical turns on the course, and then the largest radius on the course or what you expect. And you might want to go through several years worth of courses and pick these things out. And then mark 3 or 4 circles on your test surface, and I'll show you a picture in a couple slides, and lay those circles out so that you can connect them with a course. So here's an example. This is, I think, the 2014 Nebraska course, right? Here's a list of the, or here's a diagram of the course. You can see here, like a very long course. So they did not list the radiuses, but they listed the expected miles per hour at 1.9 Gs in each course. So it's easy to figure the radius from that. So I figured that out with a simple spreadsheet. The maximum was about 105 feet. The minimum was 22 feet. You might also want to look in the rules. I think they throw something in there. Your car should be able to turn below a certain or at a certain minimum radius. You might want to pick that one. And then the median and the average turn. So there's, 4 pieces of data that kind of summarize that whole course, right? You could plot out the number of, or the radius by the turn number. You could get some ideas there, or maybe a histogram by turn radius. You can see a lot of them fall in this part of the plot, or you can do a cumulative histogram and look at it that way. So in this example, most turns are less than a 50-foot radius. 65% of them are less than 50-foot radius. So that's probably a good place to focus, right? But you still would like to have that tightest corner and the biggest one. And then again, this longest corner that you're going to spend probably the most time in, that's an 80-foot radius. So that might be one to consider for your course. So based on that analysis, you want to set up 3, maybe 4 circles in a way that you can either drive around them continuously in a skid pad type test, or you can link them together to make a little miniature autocross course, right? Pick the smallest, the largest, and then 1 or 2 of the middle radius turns. So you want to start out just doing steady state cornering. Go around the smallest circle, increase the speed until you reach the limit, and then do it in the opposite direction. You can measure either lateral acceleration as a metric or lap time to complete a lap around the circle. One little caveat, this will wear your tires pretty quickly, so try not to do a whole bunch of laps, right? And because this is such a tight, slow corner, aerodynamics are not going to have a big effect. So now you want to improve that cornering speed or lap time around the corner. Here's a list of the things you can look at, and they're in order from the easiest to the hardest, right? So tire pressure is pretty easy to set if you remember to bring an air compressor or an air tank, right? Part of that planning. If you have stabilizer bars, especially if they are adjustable, it's easy to change the roll stiffness distribution. And then your static alignment, you could change camber and toe to affect that. Your Ackerman geometry gets into a little bit bigger changes to the car. Changing that, especially in the small diameter turns, will help. If you have a tunable, adjustable differential, right, that's a good opportunity. Not many teams ever touch their diff, but that can be a pretty big tuning knob. Then you get into more difficult things. Camber curves, that's really your suspension geometry. Toe curves, again, suspension geometry. Roll center heights, suspension geometry. These are not things that are easy to change out at the track. And then the center of gravity height. That's a huge knob in handling, but you can't really change it, right? You can't unbolt the center of gravity and bolt it on lower in the car. So that goes all the way back to vehicle design, right? If your center of gravity is just way too high, you may have to repackage your car, right? Can we move things lower in the car? Can we take things out that are up high in the car? So that's very hard to change, but tire pressure, obviously pretty simple to change. Okay, and then you're going to do the same thing again. Go to your next largest circle or circles. Repeat the same thing. Go around the circle at increasing speed till you reach the limit. Do it in the opposite direction. And the limit will probably be slightly different left to right. That's very common. It's tough to make a perfectly symmetrical car. And now, depending on the radius of that turn and the amount of aero you have on the car, if any, the downforce may start to come into play there. And again, you're going to go through this list. I want to improve the speed in that turn, right? And it's kind of the same list with possible aerodynamic effects thrown in there, right? And you can affect that by changing your wing angles front and rear. If you have a full underbody, there's not a lot of adjustment you can do to that, but you can use your wings to fine tune your aero. And again, the center of gravity height, that's going to be tough to change, right? And some of these settings in the bigger corner, the higher speed corner, may differ from what was optimal in that small corner. And don't worry about that. Just go with it. Then you get to that biggest circle, right? And you're going to do the same thing yet again. But it's pretty large diameter, higher speed. You're definitely going to have aero effects there if you have wings and under trays on your car, right? So the list is essentially the same, but now aerodynamics has a bigger effect, right? And that's where you can tune in your aero system.
Hey, Darrell.
Yeah.
There was the question in the chat. Didn't see on that list damper tuning.
That will come up in about a week. We'll talk about damper tuning, I think, next Friday, right? That's the next presentation.
Okay.
But yes, that's a good question. That will be on here. But this is also steady state. So your dampers have very little, if any, effect on steady state handling, right? So we'll get to that in a minute briefly, and then next week we'll go much deeper into that.
All right, thank you.
Okay. So now we've done our steady state cornering on 3 or 4 different radius turns. You may have different settings between the 3, and that's okay. You've got those documented, right? If you want to go back down and optimize for the smallest turn, you just look through your notes, what worked the best on that, right? Because you've got good notes. So then you may want to look at the number and radius of all the turns on the course and think about, maybe even just a very quick spreadsheet, right? Which turns are predominant, which ones are going to save me the most time and improve my lap time the most. You also want to keep up with your tire wear, right? Your tires will wear doing this and wear fairly fast doing this, grinding them around a circle. So if you have the same size tires front and rear, it might be good to rotate those. If you have different size front and rear, rotate them left to right. And the best, again, the stopwatch is the best indicator, right? You will probably be checking your tire temperatures, right? And you may not have, perfect tire temperatures that are uniform across the tire. And that's okay, as long as none of the temperatures are really high that you're overheating and degrading the tire, right? The goal is not to have optimum tire temperatures. And I think a lot of teams fall into that because it's a very easy metric to try to deal with, right? It's easy to stick your thermocouple in your tire and say, oh yeah, here's my tire temperature. So let's get that back. And you can change camber or change toe and have a direct effect on your tire temperature. So it's an easy loop to get into, right? You've got a good control system there, but it's not the best way to optimize the handling of your car. So now we move into the next phase where we get transient cornering. Take your same course and put a couple of cones 180 degrees apart on the circle, and you're going to come in. Well, I tell you, it's easier to do it by visual here. So you're going to put a couple of cones on each circle, and steady state how fast you can go around this turn because you look back at your notes from the test you just completed. So you want to approach that turn at that speed or maybe slightly below, and then make the transition from going straight to turning around, and then make the transition from cornering to going straight. So now you've got some transient conditions, and you'll repeat that through all 3 circles, and you can get a feel for, does your car have different characteristics in a transient place, in a transient condition than a steady state, and you can start to optimize that. But don't spend a whole lot of time on this. Don't invest a lot of development on it, because in reality on the course, you're not going to come in at a steady speed and go around the turn, right? You're going to come in fast and brake, and you're going to go out and accelerate or brake further, right? So this is just pure cornering, getting a feel, does the car have a lot of turn in understeer? Does the car continue understeering through the turn and out, right? To get some feeling, but you don't really need to optimize for these conditions because they won't happen during the race, right? So now you're going to start doing that, what I just said, brake into a corner, go around the corner, accelerate out of it, right? And this is where having those circles laid out into a course will be helpful. And you can drive in each direction and get different characteristics of the course, right? If you go around it clockwise, it's going to seem a little different than it did counterclockwise, right? So you want to take each corner and separate that into 3 segments: braking and turning in, steady state through the corner, and accelerating while reducing your steer angle coming out. This is a good place to start adjusting your brake proportioning, right? Front to rear brake proportioning will be critical. You want to use your rear tires as much as you can for braking, but at some point the car will start to oversteer, right? So you'll have to dial some of that brake bias out of the rear. You can start tuning shock damping. Going back to the question, you can use that to control your pitch under braking. It's not going to control your total amount of pitch, but it's going to control how fast the vehicle pitches. And pitch isn't inherently bad unless maybe your aero package is sensitive to pitch. And if you have a lot of camber or toe change with suspension travel, then the pitch comes from the suspension compressing. That may hurt your braking, right? So you can use the shock damping to tune that the rate and the initial amount of pitch, but the steady state is going to be the same. Okay, shocks only work in a transient condition when your suspension is actually moving. So you should be able to balance the steady state cornering, or you should have already balanced it fairly well from your first set of tests, that steady state cornering. As you accelerate out of the corner, the vehicle will typically understeer unless you really overdo it, and then you'll get oversteer. So you can tune the damping and the roll stiffness distribution, and rear alignment can be a very powerful tool, the camber and toe of the rear wheels. And you can tune the differential to help you with that acceleration out of the turn. So again, now you've linked all your 3 corners together, right? You could go around it this way and it'll be a different course from going around it this way, right? Here, you're going from the fastest turn, probably getting up to your highest speed on this straightaway, and then going into the slowest turn. So you have the hardest braking this way. Whereas here, it's kind of the opposite. You're coming out of the slowest turn and you're going to accelerate as hard as you can up to this turn and not need to brake a lot because you don't have room to accelerate. So you could get, even with this very simple course, it really becomes 2 courses by changing the direction, and you can get a variety of combinations of braking, acceleration, and cornering. So getting a little more sophisticated than this simple 3 or 4 corner course, you can have linked corners, right, where you go from one corner directly into the other with no straightaway, and that can be very transient, right? I'm turning hard left and then I immediately turn hard right, and that's where damping can help a lot there, tuning your shocks, and your driver smoothness can be a big factor there too. That's a good way to practice good, consistent driver input, steering inputs. Slaloms are also good if you just set up 6 cones in the row and the driver drives back and forth, from side to side, left to right. That can really help with driver smoothness, and it also help you with tuning these transients. The decreasing radius turns can be tough, right? Because you're already in a corner, and if you're cornering at your max capability and now you need to slow down, right, you're going to run out of friction circle from your tires. So the driver, mentally anyway, needs to work backwards. What's the slowest speed that I need to make it through this decreasing radius turn? And then kind of work back, well, I need to be braking, so I need to be going this speed and and work backwards to the entrance to that decreasing radius turn. So you may have to slow down more than you need to initially, so that you can actually slow down at the tightest part of the turn. So that's a challenge to the driver, right? And it's a good thing to have that experience. So that might be a good thing to set up a decreasing radius turn, or two turns, a large radius turn connected to a smaller radius turn. Stability under braking is important there, right? And typically you want to move your brake bias more towards the front, less towards from the rear. And then increasing radius turns are kind of the opposite, right? They combine cornering and acceleration, right? A lot of times having more front roll stiffness and less rear roll stiffness can help transfer less weight across your rear tires, give them an advantage in grip, so that they have some grip left over, some friction circle left over for longitudinal force, for acceleration. They're not being used up totally for cornering. Okay, so to wrap this up, summary of all this, of all these 50 slides or whatever, you want to take a structured approach to developing your vehicle, right? Make sure it functions, make sure it does what it's supposed to do. And the more you can do that up front with bench testing, or maybe testing parts on your old car, the better off you'll be. Then you want the reliability, right? That the vehicle will consistently, dependably start up and run and do what it's supposed to. And reliability gets a little tougher to develop on the bench, right? So the more miles, the more laps, the more tests you put on the vehicle, the more reliability issues you will find and have an opportunity to improve, right? And then the durability. Again, durability is not huge for Formula SAE cars, but it can be a factor, right? So you want to make sure your vehicle is maybe able to complete the competition twice, right? Without any major fixes or repairs, right? You want to be able to tolerate the wear and use that will come through that competition and still have a car that performs well. And then last of all, work on the performance of the vehicle from a system and from a whole vehicle standpoint, right? Improve everything you can. And we focus mostly on handling in this presentation, but the same thing applies to your powertrain, whether it's electric or gas or ICE, right? You can follow the same generic process. Obviously, the cornering isn't important, but you want to do the same thing with basically every part on the vehicle. Okay, so some references. The Learn and Compete books. Learn and Compete Volume 1 was out for a long time, and then it was out of print. It has been reprinted. And then there's a Volume 2 that is not just an updated version. It's a new book. It has a little bit of overlap with Volume 1, but it covers different topics. These books were written by design judges and industry experts. They're the only two books out there really on Formula SAE, so they're really valuable resources. I highly recommend getting a copy of them. I wrote one of the chapters in Volume 2, but full disclosure, I don't get any royalties from buying the book. I'm just recommending you buy them because they will help. They will be good for your team. And then the Fundamentals of Dynamics book by Tom Gillespie. That's kind of the Bible of vehicle dynamics. You can't go wrong with that book. The book I read just recently, this Think Fast, the Racer's Y2 Guide to Winning, is very good. It kind of covers both worlds, the practical of what to do to your race car, but also the engineering, why you want to do it, and some understanding of what it is. So Neil Roberts is an engineer, actually an aerospace engineer. He raced Formula Ford cars for a long time and did very well. He also worked for Swift designing Formula Ford cars. So he's kind of got the whole gamut of experience from behind the wheel to behind the cab tube. And that's a very good book. And then these presentations are again on the Detroit SAE chapter YouTube channel. You can go through those. And again, what's great, I'm not telling you anything magic here, but it's tailored to Formula SAE. So hopefully it will be more useful to you than reading, say, the Race Car Vehicle Dynamics book. Good book, a lot of good content, It's very dense. It's hard to just pull stuff out of, but it's a good book. It takes a lot of work to really absorb that and apply it. And then I mentioned the performance or the failure mode and effects analysis, doing that, performing that for your vehicle. Just a little tidbit that you will impress at least one design judge, me, if you have a failure mode and effects analysis for your car. And you don't need to devote a whole lot of time to it. You can get very sophisticated in how you do it, but the key thing is it's a structured approach to thinking through everything that could go wrong with your vehicle and how likely that would be, how severe that would be, and to prioritize it. So here's the worst things that we need to worry about. Let's go fix those. And here's things that, yeah, they could go wrong, but they're not likely to go wrong. They won't be severe if they go wrong. We don't need to sweat those right away. But it's a great way to kind of prioritize what you want to be working on with your car. When I first was doing that in the late 80s, it was, this magic new process. And I took a bunch of training and I said, well, this is really nothing other than what a good engineer does in his head. You're just forcing a little discipline and focus on it and documentation of it. So it's not magic, but it is a very good process to follow. Okay, so that wraps us up for today. A couple of upcoming seminars. February 3rd, next Friday, I will do the same kind of thing again, but for shock tuning. I tuned shock absorbers on Indy cars. I worked as a shock absorber design engineer for a few years, so I got some background there. And I'll try to cut through all the mystery of shock absorbers and help you tune them. And then a week after that, we have a presentation event overview that should help prepare you for the presentation event that will be part of the competition. Okay, so that does it for me. Looks like we're pretty much on time. Any more questions, Tim?
It's been kind of quiet in the chat. So I think that, there's a lot to you've given a lot of good experience, a lot of practical advice here. Let me ask, if you only had one day, like, oh man, we just got the car together, we got one day to test, what would you recommend?
I would do the steady state cornering, right? That's the foundation of all of your handling, right? If your car won't drive around a circle, you're not going to fare well in the autocross or the endurance competition, or even the skid pad competition. And that's something I guess maybe I should add to this presentation. The skid pad competition for Formula SAE is kind of weird. It's more of a figure eight competition. When you say skid pad, you typically think of steady state handling, but obviously there's a transient aspect to the Formula SAE event, and that's something you may want to duplicate. You may want to set up that course and practice on that a little bit, both for driver practice and for developing the handling of your vehicle. A fair number of points in that, and a somewhat unique handling situation. So that's something you might want to preview in all of your development of your vehicle.
That's good. It's a good point. And I'll just bring up because I'm a simulation guy and I have to. It's probably good to, when you talk about instrumentation, think about, what is the minimum amount of data you would need to validate if you're using car sim or car maker or Optimum G or anything, or your hand calculation, Excel calculations from your first principles, what is the minimum amount of data that you would need to validate your equation. So think of that, think about that as well. I was just chatting, one of our attendees here, Gary Gadula, and Gary, I hope I pronounced your last name right. Gary is as I found out, is a team captain for the practice area at the MIS events.
Oh,
and so they have when you go to the competitions at MIS and they have the practice area, you can go in and his team, he and his the crew will help with some of the help you, give you a little bit of guidance for your testing and practice. So I thought maybe if Gary doesn't mind, we can unmute him and maybe he could just make a few comments about what he and his team do at the events.
Yeah, that would be great.
Yeah. So Gary, if you want to, we can.
Yep. Darrell and Tim, thank you.
Yeah.
Great. Excellent presentation. Most things right, a couple things wrong, but as far as to the event and everything. But yeah, the biggest, when we're down in the practice area, we're basically trying to prepare the teams for competition. And so we're trying to clean up as many issues as we see as possible, particularly leaks, bottoming, anything flapping around, anything that can cause an issue at the events. Sometimes that involves a lot of chassis tuning and coaching. Sometimes it involves some driving coaching. So we're open to help anybody. Tim, I sent you the layout of the practice area that we've used for the last 5 years, and I was curious on your input on what's the best way for the teams to utilize that. The biggest mistake we see out there consistently every year is teams not putting anti-roll bars on their cars, front or rear. Yeah. And without the anti-roll bars, you cannot tune your lateral load distribution and balance the car without compromising, making a lot of other compromises in pitch and work.
Yeah, I have to say I was surprised by how many teams did not have front and rear stabilizer bars or anti-roll bars.
And what we'll see consistently is those cars will just, in a steady state corner, will roll and roll and roll and roll and understeer until it tucks the outside front tire into the suspension and the rear of the car comes swinging around. And the driver says the car is loose, the car is oversteering. No, it's understeering like a pig. And you can fix those things by putting anti-roll bars on it to keep the front suspension in alignment. It's just rolling outside of your design window. So also do a lot of shock tuning. And the big thing there is I encourage the teams to try things. Yeah. You think the car is good, change something. Change the anti-roll bars, change the shocks, change wing settings. Play with the car. As long as you're writing it all down, if it doesn't work, you can change it back. And then you know what not to do later on.
Yeah, I have to agree. I'm surprised, most teams have the 4-way adjustable Olin shocks and they've never adjusted them. They're afraid to touch those knobs.
Now, the practice area that we've been utilizing has elements of all the competition events for the teams. We have an acceleration lane. It's only 65 meters, not 75, best we can package, but you can practice your acceleration procedure because driving wise, it's a procedure to launch a car. We have the skid pad, a single skid pad to scale, and it's on the same competition surface. We have a short autocross that we try to present the autocross the same as what you would see on track, so your drivers can get used to the visuals of following a course with their eyes. And then we'll throw about a 7-cone, 40-foot space slalom on the side. And they can, all these areas stand independent, so they can loop it all together and create whatever sort of lap they want, with those elements.
Yeah, that's great. I mean, it's a shame you can't do that, for a month before the competition to give everybody the chance to make bigger changes to their car, right? Once you get to the competition, it's so limited what you can do to your car.
Yeah,
right?
your performance envelope is pretty much defined at that point. All you can do is make the car as consistent and easy to drive as possible so you can get to that limit as consistently as possible.
Yeah, so that's a great point. You get to the competition, you've got this practice area available, you've got some expertise available to you there, and that's fantastic. But you could have been doing this all along, right? For a month or 2 months beforehand, and had the opportunity to make some bigger changes to your car.
Agreed. So that's all I would have is I really want to emphasize, get the cars done early. Your top teams have probably got running cars right now outside of the European teams their cars were built last year. Your top teams are probably pretty close to having a running car and probably have something on the ground by Valentine's Day. and then they're just spending the rest of the time to competition refining that car and not being overloaded between the development of the car and the rest of your school curriculum.
Yeah, when I was in college, we competed in the Baja,
Mhm.
and absolutely the best year we had a running car before we went home for Thanksgiving. You know, it was far from complete, but we could drive it around, you know, before Thanksgiving, and we found so much room for improvement in that car, and we essentially rebuilt the whole car by competition, and it was not the fastest car out there, but it ran pretty well, and it completed every event in the points, right up. We didn't win any events, we didn't win overall, but we had a pretty high overall score just because we were ready.
Mhm. Yep, that's what I see from a lot of teams, and like I said, that's their plan is to have cars running in February. I see that from, I'm on the alumni list for a number of teams. So I see how they're preparing.
Yeah.
Yep.
Hey, Darrell, we got a question in the chat.
Uh-oh.
So yeah, Darrell Reagan, I hope I pronounced your name right. He's from North Carolina A&T and the Aggie Racing Baja team as a shock question. He says, is there a heavy emphasis on having stiffer shocks and springs in the rear rather than the front?
Well, I already said the answer to this question. It depends, right? And everything is a compromise.
Yep.
So it will depend on what's the weight distribution of your car, what your spring rates, what your ride frequencies are, right? In general, the damping will kind of go hand in hand with the ride frequency. But the best answer is try it, right? I don't know if you have adjustable shocks. If you do, that's an easy change to make, right? Give it a couple clicks. If that doesn't work, well, give it a couple clicks back, right? Then try a couple clicks in the other direction. So, there are some basic calculations you can do out there that will get you in the ballpark. Yes, the Fundamentals of Dynamics book. Also, the Learn and Compete book. There's a very good section on shocks in volume 1, written by Jim Kasperzak. So you can do some calculations that will get you in the ballpark. And then if you have adjustable or rebuildable shocks, you can kind of iterate around there, right? The problem is you don't want to start out in left field and make a bunch of changes. If you can get yourself in close to where you want to be and then tune from there, that's probably the best approach.
Yeah. And I think Darrell from North Carolina A&T, the fact that your vehicle, a Baja car, may want different springing, different ride frequencies front and rear than say a Formula car, just based on the type of surfaces and maneuvers that you're going to be doing. So
hopefully that was a good enough answer. Probably not down to the dotting the last I and crossing the last T, but part of that is your job to figure this out as a student, right?
Yep.
Then in a few years you can be putting on this presentation.
Yeah. Let's see. So he says, okay, thank you all. I'll attend next week's session for more information. Excellent. And tell your friends.
Yeah, spread the word.
Spread the word. Okay. Anybody else? Any questions, comments, interesting anecdotes? Okay. All right. So yeah, thank you. And I guess like you said, thanks for joining today. The video will probably be posted on the Detroit section YouTube channel here in the next shortly. And we hope to see you next week for the Darrell's presentation on shock absorbers. So
yeah, so please go and view this video. Tim and I are having a little competition on who can get more views of their videos.
Yeah, the Kingpin Axis one and the tire one is worth looking at too. So, all right. Well, thank you, Darrell. Thanks for sharing all your expertise and knowledge, and we look forward to the next session.
I'm glad to do it. Thanks for helping out, Tim, and thanks everybody for coming today. Just a little feedback. You are absolutely doing the right thing by getting involved in these student competitions. You're learning things you would not otherwise learn in college, and you won't realize how much you got out of this competition until a few years into your career. I mean, I've worked on everything from GTP cars to Indy cars, and the lessons I learned doing Baja are still valuable today, 40 years later. Okay, thanks everybody. We'll hopefully see you next week.
All right. Thank you. See you.